Okay, so hi everyone, welcome to this new edition of the probability seminar, Chilean probability seminar. This time it's a pleasure to introduce Alexander Drewitz from University of Cologne, who is going to talk to us about percolation and long-range correlations. So, todo tuyo, Alexander.
Well, thank you very much for the invitation and also for the introduction. It's always very nice and a pleasure to be in Chile, this time only online, but still. So I'm going to talk about the percolation and long-range correlations. And this, essentially all of what I'm going to talk about is joint work with Alexis Prévost, who was my PhD student, and he's now doing a postdoc in Geneva, and Pierre-François Rodriguez, who's at Imperial. So in case you do have any questions, please don't hesitate to interrupt me, and well, wherever. So really feel free to interrupt in case there's anything which is not clear. So as the title suggests, I'm going to talk about some problems concerning percolation, including long-range correlations. And for that purpose, I'm going to introduce the basic setting of Bernoulli percolation, which is presumably known to most of us. I'll review what's known, what is not known, and that is sort of setting the frame for what we're going to investigate in these percolation models, which include long-range correlations. So, well, arguably one of the simplest models of percolation is that of Bernoulli percolation, and here we stick to bond percolation for the sake of definiteness. And so this model has been introduced actually by chemists in the last century, so that was in the 1940s by Flory and Stockmayer, who were investigating gelation. So that means as molecules accumulate, they form bigger and bigger polymers. So that's something, for example, that you can also observe when you're boiling an egg. So when you have low temperature, it's sort of liquid, and then you increase the temperature, it starts getting solid. And so later on, also Broadbent and Hammersley investigated this model in their research on gas masks. And there's, well, many further applications, like, for example, preparing coffee is one of the, I guess, most popular examples in that context also. So the question is, how dense can you put the coffee, or so that you still have water percolating through, so you get an espresso after all. Now, the model essentially consists of assigning each bond in ZD to be open with a probability P and to be closed with a probability 1 minus P. And that's going to happen in an IID fashion. So everything's independent from any other edge. And one of the questions that you're interested in is the existence of either only bounded connected components if you're in the subcritical regime. This one here. So if you're smaller than PC, or you can show that for this PC, which is strictly between 0 and 1, if you're larger than this critical parameter, there exists a unique unbounded connected component. So from that point of view, there's a phase transition happening. That means for values which are smaller than this critical value, you're subcritical, you only see finite connected components of open bonds. Whereas once you're supercritical, you do see that there's an unbounded connected component emerging. So in terms of pictures, if you're in Z2 and have a look at bond percolation, so that's a realization of P equal to 0.4. And this is obviously not an infinite lattice, but only a finite subset of this. So you won't talk about an infinite connected component, but you can, for example, ask whether you can actually go from the left to the right part of this rectangle by just using the black edges, which are the open bonds, right? And if you try to do this, then you observe that, well, in this realization, you won't be able to cross from left to right just using these open bonds. So you can increase the probability. And if you're at P equal to 0.5, then you can ask the same question. So do you find a path from the left part of this rectangle to the right part? which just uses these black bonds. And so this is actually not so easy to recognize anymore in this realization. And the reason is that P equal to 0.5 actually is the critical value, right? So that's PC if you have a look at bond percolation in 2 dimensions. And that's very special also because in general, PC is not known, right? You can show that it's strictly between 0 and 1. So that means you do have a non-trivial phase transition occurring. But the explicit value of this PC is rarely ever known. So here it is, and this is actually the critical value. So it's not so clear whether you can go from left to right using open edges. So if you increase P a little further, then you see that if you're now trying to solve the same problem, that means going from left to right, just using black bonds, well, then you find actually that there do exist many paths which actually accomplish this, okay? So that's how you go from subcritical to supercritical regime in that setting. And so if you consider in general Bernoulli percolation on ZD, so not only D equal to 2, but also higher dimensions, then as long as you're in the off-critical regime, this is pretty well understood these days. So that means, for example, if you're in the subcritical regime, you do know that the phase transition is actually sharp. So that has been a result proven by Menshikov in '86, and then also by Eisenman and Barsky in '87, where sharpness, well, in the sense of Menshikov here, you can define it as follows. So that means once you're subcritical, so you know that you don't see an unbounded connected component, you actually get that the probability of connecting the origin to the boundary of a ball of radius n decays exponentially in n, right? So there's no intermediate regime. So once you know that the probability of seeing an unbounded connected component is 0, you already get the exponential decay. So there's nothing, no intermediate regime in which, for example, a polynomial decay of this quantity could occur. Now, in particular, that implies that this expected cluster size of the cluster of the origin, so C0 is the open cluster of the origin. That means all the edges which are open and which are connected to the origin by just using a black path. That means a path consisting of open edges. And if you consider the expectation of this thing here, then as an immediate consequence of that one, you get that the expectation is finite. And so this also refers to the sharpness because, well, historically, there's been 2 critical parameters. One was the PC I introduced, and there was another one which was actually investigating the finiteness of this expectation here. And it wasn't clear whether they coincided. So what Menshikov and Eisenman-Barsky did was they actually showed that these 2 parameters coincide. So also, if you're in the supercritical regime, a lot of properties are known. So I just named a few here, which is by far non-exhaustive. And if you're interested, say, in what's known in the off-critical regimes, then one of the standard sources certainly still is Grimmett's book, even though it's almost like a quarter of a decade old by now. So long thing short, when you're in the subcritical or supercritical regime, Bernoulli percolation is pretty well understood. Okay, so once you get closer to the critical value PC, less is known. So, for example, you do know, as I was saying in the introduction, that in the 2-dimensional planar Bernoulli setting, you do actually have that PC is 0.5. So that's a result due to Keston and Harris, and there's also no percolation at the critical point itself. So this is important, and we'll come back to that later on. So also, if you have a look at very sort of special lattices in the 2-dimensional plane, such as the hexagonal or triangular lattice, it had actually been shown by Smirnov and Werner using conformal invariance that certain critical exponents for Bernoulli percolation are known. So critical exponents are quantities that actually describe the behavior of your percolation model close to the critical value PC. So we'll come back to this later on as well. But keep in mind that in the 2D setting, in certain special lattices, things are pretty well understood for Bernoulli percolation. And also, once you go to higher dimensions, where higher is supposed to, well, or conjectured to be 6 or larger, Hara and Slade actually used laser expansion to investigate the percolation process close to its critical value. So that's the mean field regime. As I said, supposedly it's dimension 6 or larger, but I think the state of the art currently, which is mathematically proven, is dimension 11 and upwards. So in this setting, percolation in these high dimensions is sort of behaving like percolation on regular trees, for example. So the nice thing here is that in general you don't see loops, so that makes computation of quantities much easier than if you're in the Euclidean lattice in lower dimensions where you do see loops occurring. So as I was saying, you do know that in 2D percolation at the critical point, you don't have percolation. However, once you go to 3 or higher dimensions, it's not known whether this still is true. So that's what I'm writing here. So theta of PC or theta of P is the percolation function. So that's the probability that the origin is connected to infinity by one of these black components, of which we know there's only one, in fact. So that's the probability of percolation. And we know that for P smaller than PC, it's 0. We know that for P larger than PC, it's strictly positive. But what's actually happening at the critical point here is still open. So people do expect that it's actually 0. So you don't have percolation there, right? So you do have that theta actually is a continuous function. But as I said, that's that's essentially the basic open question, or the seminal open question in this field, right? So this certainly also shows you that at the critical point or around the critical point, even in the sort of simpler setting of Bernoulli percolation, there's still quite important results or quite important conjectures which are still not known. Okay. So do you have any questions so far? I mean, up to now, I've been introducing or sort of recalling what's known in Bernoulli percolation. And so as the title suggests, we'll have a look at a different percolation model, which is in fact induced by the Gaussian free field. So the Gaussian free field, we'll consider it on a graph, which is a transient, countably infinite, and we also can put symmetric weights if you want. But otherwise, the results are also new if you just put ZD, D larger than or equal to 3. So what you then consider is simple random walk on that graph. So that's just the Markov chain where the transition probabilities are given by this quantity over here. And so then one way to define the Gaussian free field on this graph G is to say, well, the GFF is the centered Gaussian process with covariance given by the green function, right? So if I have a Gaussian process, I know its mean and I know its covariance, then that's completely characterized. So once we say it's centered and we say the covariance structure is given by the green function, that's already characterizing your GFF. Okay, so this is just the expected number essentially of a random walk starting in X that it spends in Y before escaping to infinity. And there's other ways to view this. So if you consider a finite subset of ZD, you can also say, well, then the GFF is nothing else than the field which is has a density proportional to Lebesgue measure by this density over here. So that's one of the reasons why it's actually also referred to as a d-dimensional analog of Brownian motion, where the d-dimensional refers to the index set, because we are considering subsets of ZD here. So it also has the property that this covariance only decays algebraically. Right? So we know that the green function gxy, as x and y get far apart, it decays like the distance to the power 2 minus d. So that means it's pretty strong correlations. In Bernoulli percolation, if you were considering here, say, open or closed for one edge, or side, for example, and here for another one, then you will just see that it's already independent. But here you get a structure which is sort of very dependent, in fact. And so here's a picture by Laurent Coquille. So that's two-dimensional. So we put boundaries, but you know, it's harder to draw if you wanted to do it in 3D. So here you just see you get this random surface, right? You also see that, so that's the black lines in here. Well, that's essentially, these are just the integer points. So what you get is this grid. So we evaluate it at the intersections of these black lines, and then you see that you get a very rough surface over here. So that's essentially a random surface. And what we are interested in is the random subset that is induced by the excursion set of this field in higher dimensions, obviously not 2D, but strictly larger than 2. But essentially what you have a look at is you have a look at the excursion sets of this random field, and you ask similar questions to those which have been investigated in Bernoulli percolation. So that's what we are trying to do today. So as I said, if you do so, then you get these excursion sets. So that's just the random subset of the underlying graph at which the field takes values larger than or equal to h. Okay. So again, for Bernoulli percolation, the phi x will be IID random variables Bernoulli, and you could, okay, I mean, well, I mean, you could also interpret this as a height function for the Bernoulli setting, but then you would just have that any of the phi x is independent. So here, again, you have these long-range correlations. And it's a little bit like, if you see this for the first time, it's a little bit getting used to it, because if you increase h, this set here is actually getting smaller, right? Because you have less vertices which are contained in this random subset of G, because there's less values where phi x is larger than or equal to h if you increase h. So sort of a little bit reversed when you compare it to Bernoulli percolation, because if you increase p, you saw more open edges. So therefore, you also change a little bit or you adapt sort of the definition of the critical parameter. So you can say it's the infimal h in R such that the probability of the excursion set having an unbounded connected component is 0. So if you decrease h, then you see that EH is getting, or E larger than or equal to h is getting bigger. So at some point, the probability of seeing an unbounded cluster might get positive. Now that problem, or that model, has first been investigated by Leibowitz and Salur in '86. And it has then been shown by Bricmont, Leibowitz, and Maas that this critical parameter h star is actually non-negative for any dimension larger than or equal to 3. And they were also able to show that h star of 3 is finite. So that means that in 3 dimensions, they actually established the existence of a non-trivial phase transition. So then it took quite some time for things to develop further. So it was Pierre-François Rodriguez and his supervisor, Alessandro Snitman, who showed that h star of ZD is actually finite for all dimensions larger than or equal to 3, right? So that sort of complements or extends this result to any relevant dimension here. And they also showed that h star of ZD is strictly positive for large D. So this result, I mean, h star being strictly positive means that it corresponds to PC being smaller than 1/2, which is a classical result by Campanino and Russo, which essentially tells you that at the critical point, you do see multiple phases. Namely, you do have an infinite component below h, and you also do see an infinite component above h if you take these two level sets. So then with Pierre-François, we had a look at the asymptotics of this critical parameter h star of ZD, and showed that it behaves like this quantity over here, which essentially is also comparable to Bernoulli percolation. Because if you have a look at the critical density, it's essentially like 1/2D. I mean, we didn't get that precise because we have this little o of one term in here, but at first order, that's what this tells you. So then with Alexis and Pierre-François, we also showed that in fact, H star of ZD is strictly positive for any dimension larger than or equal to 3. So that sort of extended the result, which here was only shown for large D. And this here was essentially done by considering the GFF in high dimensions as a perturbation of an IID field. And we used completely different techniques involving isomorphism theorems. And I'll get back to isomorphisms later in this talk. So then it was Hugo Duminil-Coupin, Goswami, Rodriguez, and Severo who showed that the phase transition for the GFF level set percolation is in fact sharp as well. So there have been several critical parameters similar to the history of Bernoulli percolation, which in fact turn out to be all identical. So that's what this sharpness result here is about. Okay, so these are off-critical results for this discrete GFF level set percolation. And so again, with Alexis and Pierre-François, we also had a look at sort of more general graphs, in particular prefactal graphs. So where we essentially showed that this guy here is actually positive as long as you're in dimension strictly larger than 2 in some sense, and G being sufficiently regular. And one of the nice consequences of this was that it also settled the non-trivial phase transition for the model of random interlacements. So that was something that had been conjectured by Snitman a little bit more than 10 years ago. And using isomorphism theorems, we also could transfer this thing here to actually getting the non-triviality of the phase transition for vacant set percolation of random interlacements. So I won't go into the details of random interlacements because it's a little bit intricate, but I wanted to mention this as a side note at least. And we also cover, as I said, certain prefractals. So one of them being the Sierpinski triangle, which I drew a finite subset of it. So that's not yet transient. We need transient graphs. So what we can do is we can take the product with a Z. So then you get what is called the Toblerone graph, because you just take the product with Z of this guy over here, and it sort of resembles what a Toblerone chocolate bar looks like. We can also treat other prefactals such as the Sierpinski caplet. Okay, but this is just for sort of completeness. So what we are having a look at today is not the exact model that I introduced before, but we will sort of embellish it by adding a continuous structure, right? So before I was talking about having an infinite graph, but countable. So, I mean, ZD, D larger than or equal to 3 would work. That's what I said. And what we can now do, and this is what's going to happen here, is we introduce what is called the cable system, which means essentially just that you add between any two neighboring vertices of your graph, you add a line segment. So this really makes it like a continuum structure. And so this construction goes back to Varopoulos at least, but it had sort of been reinvigorated recently in the setting of the GFF by Titus Lupo. So he was bringing this in this context here. Right, so essentially what you're doing is, so if you, let me draw just a little. Right, so if this here is a subset of ZD, then what you do is you really add line segments between any neighboring vertices, and you continue this for the entire lattice. And the nice thing is that this in some sense brings in analysis, because what you do is you consider your GFF still on this discrete lattice, and then you extend it to these line segments by adding Brownian bridges, right? So maybe, let me here, maybe I do this here. So if this here is now our cable system, and this here is the value of the field, then I had it at these, if this here gives me the value of the field, then I extend it to this cable system. Let me do it in the red here by saying this is actually the Brownian bridge, going from one endpoint or the value of the GFF at the endpoint to that of another one. So let me call that one X here, or maybe do it in black, that one Y. So then here I had this one here gives me phi of X, that's phi of Y. And in between, I interpolate using a Brownian bridge. Okay. So the nice thing is that it turns out that in these isomorphism theorems, there is the square of the GFF. And if you take the square of some, it's on the discrete graph, it was a countable family. It was a countable family of random variables. And if you take the square, it'll always be positive. But so here, if you do the same thing on this continuum structure, you see that you can actually detect a sign change of the field because, here the square would be positive. It would be positive here. But since in between you have a continuous function, it has to cross zero. So it has to vanish at some point. And that's something that turns out pretty useful in this setting of isomorphism theorems. So that's the reason why this will be useful in the end. All right, so okay, so another interpretation is to say, you can realize it phi x, phi y first, and then you say that a bond is open if the Brownian bridge that goes from phi x to phi y always stays positive, right? So here, that bond would not be open just because phi y would be negative already, but assume that phi y was, was that value here. And then you could have a Brownian bridge that either, does like this. So then it would not be open because it's sort of crossing this value 0. Or you could have a Brownian bridge that goes like that. And so it stays positive on the entire line segment. And then you would call such an edge open. So by doing so, you get a percolation model, a bond percolation model, which has long-range correlations. So if there's any kind of question, please ask. This is the model that we'll be dealing with, right? So we start with this discrete GFF, and then we interpolate on the edges, just adding these line segments.
So in this model, there's no parameter, I guess.
Exactly.
Okay.
The parameter is the height. We'll have a look at the excursion sets above a certain height, and that's the parameter we look at.
Okay.
And you can do it the same thing in Bernoulli percolation if you put uniform random variables uniformly on 0, 1 at any side or any bond, then you have a look at the excursions, and that gives you a random subset with essentially parameter 1 minus p. So it's just in Bernoulli you don't do it because you can do it simpler, but here we use the level as the parameter.
Yeah, sure. Thanks.
All right. So now the kind of objects that we're interested in, again, they are motivated by what I introduced before in the context of Bernoulli percolation. So the excursion set is just the random subset of now this continuum cable system graph. All those vertices where the field takes values larger than or equal to h, right? So this is now a subset of this continuum graph. We'll also have a look at the cluster of the origin, which is sort of analogous to what we've seen also in Bernoulli percolation. So we ask, which are the vertices in the cable system that we can connect using just path which only see points, or which only see points in the cable system at which the field takes value larger than or equal to h, right? So we'll also have a look at a certain function theta, but it's we call it, well, we define it to be the non-percolation function. such as this here. So the probability that the excursion set above H is actually bounded, the one containing the origin. So the reason is that this way, if you do it, okay, I mean, I said you had this kind of, I mean, Bernoulli percolation was increasing in P. This here is decreasing in H. So that's the reason why we talk about non-percolation function, because then, oops, let me do it like this. So because, you know, if you have a look at something like this over here, then we will later on see that the function actually, so that this theta tilde looks actually like this. So it's 1 over here. It converges to 0 over here. And then the question is what's happening here. I mean, and as you see, so it's a bit implicit, but this is actually, let me do it like, so this is H. And it turns out that this critical parameter for the cable system, H star, is 0. But I'll come back to this later. So exactly. So the way we do it now is we say, okay, in a similar way to what we did before for H star and PC, we again define a critical parameter, just analogous to what we did before for the discrete system. So, and then the functions that we'll be investigating in that setting are the radius function. So either it's finite anyways, or otherwise we have a look at the truncated radius function. That means we only consider, or we restrict to the cluster of the origin being bounded. And in a similar way, we consider the 2-point function. That is also the truncated 2-point function where, again, we want the cluster of the origin to be bounded. Okay, so these are the objects that we are trying to investigate close to the critical point. That means close to H star tilde. Now, I said before that in general, PC is not known. It turns out otherwise for H star tilde. So it turns out that H star tilde actually most of the times is equal to 0. Now that might seem surprising because in Bernoulli percolation, you do have a lot of independence. So you would assume things to be somewhat easier. However, I told you that PC is in general not known. On the other hand, H tilde star almost always is equal to 0. So you do actually have to work a little bit, which is what Alexei did in his PhD also, among other things, to find examples for which H star tilde is actually different from 0. So this is non-trivial to find examples. So any Euclidean lattice, for example, would give you that H star tilde is equal to 0. And any well-behaved, polynomially growing, reasonably nice graph as well. It also turns out that at the critical point, that means at 0, the non-percolation function is 1. That means we don't percolate at the critical point. Again, this is much more than what is known in Bernoulli percolation, because that sort of these two things here are true in very wide generality. And we'll assume them as standing assumptions. But the point I'm trying to make here is that, in fact, that's sort of the standard case. So any reasonably nice graph you come up with will actually fulfill these two conditions. We also assume the graph we're considering to be alpha-alphas regular. That means you do have regular volume growth conditions. We also want a certain regular decay of the green function. So we want that the green function gxy decays like dxy to the minus mu. So if you're in the setting where, say, we can consider z alpha for alpha larger than, let's say larger than or equal to 3. So in that case, we would have that nu is given by alpha minus 2, right? So in Z3, we would have that, okay, we do have alpha equal to 3 and nu is equal to 1. So, and that's another technical assumption, which I'm not going to elaborate on. It's not essential, right? But that's the setting in ZD. So we are not the first ones who have been working on this this model. So as I said, Titus Lupo has been certainly, he's one of the names to mention here. And so he actually showed in a very nice explicit computation that the truncated two-point function actually is quite explicit. So the probability of, of connecting 0 to x in the non-negative level set is given by this function here, which in particular implies that it decays like distance to the minus nu. Also, in the special case of Z3, Jan Ding and Matteo Wirth, they computed bounds for the truncated radius function. So they showed that psi 0r, so the probability of connecting the origin to the boundary of a ball of radius r using just non-negative values in the cable system of your GFF essentially decays like r to the minus 1/2, and then here there's a logarithmic prefactor. And for sake of completeness, let me maybe introduce here the concept of capacity. So capacity of a set is just another way to sort of measure its size. So it's not in terms of volume, but in some sense, it gives you the visibility of a set for a random walk started from far away. So essentially that determines the probability, like how probable it is for a random walk starting from far away to hit your ball or to hit your set K here. And one important quantity or asymptotics is that if you have a look at the capacity of the ball of radius r, it grows like r to the nu. So that's slower than the volume if you're, for example, in any of the Euclidean settings. Also slower than the surface, but right. So that means the ball of radius r in Z3 has capacity of order r. And it turns out that capacity for the GFF is a pretty important property, which is sort of implied by the dependence or the covariance structure of the field. So, all right. So the first thing that we obtain with Alexis and Pierre-François is we can compute the density of the random variable, which is given by capacity of K tilde H, right? So, okay, so if you choose A positive, then this guy here is bounded anyways. If you choose it negative, then this here might be unbounded, but we have a look at its truncated version. So then it turns out that the density is given by the expression on the right-hand side here. And the nice thing certainly is that we do get an explicit expression for it. And this is sort of also one of the important starting points for all the other results, because it turns out that the capacity actually gives you quite a lot of information in that context. So, for example, we do get that this non-percolation function, which is this theta tilde h, which I drew before. So, right. So I said that essentially, okay, that's here. There's 1, and here you put h. Then we know now that the critical value is 0. So to the right of it, we have that the non-percolation function is 1. And what we get here now is the following. We get that this expression here as h goes to 0 behaves like this constant here. So in particular, what we get is that 1 minus theta tilde h is a linear function, or almost linear. So if we divide by h, then this converges to a constant. So that means that if you, here we have 0. So that means that the function, if you, right, so maybe, so that's theta tilde. And to the left of the origin, it behaves in the vicinity of the critical point 0. It behaves almost like a linear function. In particular, beta is equal to 1, right? So that's a critical exponent that belongs to the percolation function. So if you've seen that before, in terms of Bernoulli percolation, you might think, oh, that might not be that interesting because it might be an indication that you're always mean field. So in Bernoulli percolation, you know that from dimension, or it's expected then from dimension 6 onwards, you always have beta equal to 1. So that's the mean field bound. But it turns out that our model is not always mean field. This is just sort of an artifact, right? But so what we can say here is for any dimension, we do get that the critical exponent beta is equal to 1, and we even get the prefactor in front of the linear function that this is approximating. Okay, so what we now do is we have a look at further critical exponents, and for that purpose, what we do is we introduce the correlation length of the system, and that's denoted by psi of h usually, and we define it to be this thing over here, so absolute value of h to the -2 over nu, and heuristically the correlation length is the length scale, how far you actually have to look in order to figure out that you're not at the critical point, but off critical, right? So that means the closer you take h to its critical point, that means the closer h gets to 0, the more critical the behavior gets, and that means the more the further you have to look in order to actually figure out that you're not at the critical point, but somewhat still a little bit off critical, right? So that's the role of the correlation length. And so we then get, recalling that psi hr was the truncated two-point function, we get that we can compare this two-point function for, in particular, that's interesting for h close to 0. We can compare it by the value, or by the two-point function for h equal to 0. And then we get these exponential these exponential factors over here, which in particular do tell us that once r is getting to the length scale of the correlation length, this exponential decay here kicks in. So that's something that's expected in Bernoulli percolation also, that you have that close to the critical point, such things here behave like the value at the critical point times an exponential, and the exponential only is kicking in once you're at the length scale of the correlation length. And this is what we are proving here. So that's for nu smaller equal to 1, for nu larger equal to 1. We don't get, well, we get upper bounds as here, and we do get lower bounds as here. Okay, so that's that. Maybe, okay, so maybe let me just mention here that we can also get similar estimates for the truncated two-point functions. And that again sort of is confirming, or that's consistent with the predictions made by physicists some 40 years ago about disorder relevance. So that's essentially the, so that's the critical exponent gamma that we get over here. But maybe let me, due to time running, go to the next slide, which is a bit more instructive, I guess. So here I drew a sketch or a table to explain, in particular, comparing to Bernoulli percolation, what we did, what we got, and what is known. So first of all, let me start with recalling that there are certain scaling relations or hyperscaling relations. So these are relations involving the different critical exponents, right? So I won't introduce all these critical exponents. I introduced beta before. So that was the critical exponents belonging to this percolation or non-percolation function. And so that is that one over here, the one concerning the percolation probability. And in a similar way, you can introduce other critical exponents. And there are certain, there's certain arguments which lead to these scaling relations, which are more or less well established. And there's also hyperscaling relations, which are a bit more, or say, less established, right? And so what we get is the following. We have in the first line here written all the exponents. So alpha c is not the one from the volume, but it's the critical exponent concerning the clusters per vertex. And the red ones that we see in the second line, on the second row, they are the ones which we could compute in the model that I introduced before, so the GFF cable system. And then the black ones are the ones that we can get from the red ones using the scaling relations, right? Because as I said here, once you have a couple of those, you can get further critical exponents by plugging in into these scaling relations. And then down here, you do see the values for the corresponding exponents in Bernoulli percolation. Now, in particular, you see that we always have this approximate sign. And the reason being that in Bernoulli percolation in Z3, this is not known. I mean, these are all computer simulations in the case of Bernoulli percolation. So therefore, I think it's even more sort of surprising that in this a priori more complicated setting of GFF excursion sets, you can actually compute them explicitly. And okay, so one caveat for the time being is that we have to restrict most results or to the setting of nu between 0 and 1. So that means that we have a look at strictly more than 2 dimensions and up to including 3 dimensions. So 3 dimensions are included, which is nice. But for higher dimensions, we are still working on corresponding results, and things become more difficult here because in dimensions strictly larger than 2 and smaller than or equal to 3, essentially the capacity of a line of length r is similar or is comparable to the capacity of a ball of radius r. So that is helping us a lot in the analysis of the model, because in some sense you can compare lines and balls and go backwards and forward or back and forth between comparing such quantities. Another thing which is quite...
Alexander, just to read this, what was alpha?
So alpha was the one from, so this here was, sorry, that's the one from the volume growth.
Okay.
Exactly, so that's a good point. So, I mean, you see that everything that's coming in here in the second line only depends on alpha and nu, right? Alpha was the volume growth exponent and nu was the decay of the green function. That's the only 2 parameters that come in here. In particular, that shows you that what is conjectured that these critical exponents or the behavior close to the critical point doesn't really depend on the microscopic structure of the underlying graph, but it only depends on large-scale properties. And that's something that is confirmed here because alpha and nu only govern the asymptotic growth. That means the asymptotic growth of the volume or the asymptotic decay of the green function, but it's all asymptotic properties, so they don't really care about what's happening on a local level.
What do you mean by clusters per vertex? Like one vertex just can belong to one cluster, no? So what I'm...
Yeah, exactly. But it's so that is 1 over the expected cluster size, I think. So that's something that's usually referred to as clusters per vertex. So I didn't give all. So if you want rigorous definitions of any of these, well, except for the last one, this is what we introduced. But any of the other ones, you find them in Grimmett's book for the explicit definitions. Okay. so these are just the, I mean, the definition is sort of just an like a straightforward adaptation to the setting of the cable system. And then also what you see here is that if you take alpha to 6 from below, or equivalently nu to 4 from below, that these exponents do actually converge towards the mean field values for Bernoulli percolation, or say the ones which are conjecture, because well, it's not rigorously proven, but you do have simulations, and then you see that once we are at dimension 6 or higher, that is the exponents we get are the ones you get in Bernoulli percolation also, or you expect to get in Bernoulli percolation also. So the takeaway is essentially that our values only depend on alpha and nu. That means large-scale behavior, and that we can actually compute them explicitly, just yes, depending on these two. So, okay, let me focus on the lower bound, because I think it's a little bit more instructive and more pictorial, I would say. And since time is running out, I don't want to stretch you any further, or your patience. So, so what we want to show is we want to get here a lower bound for the radius function, right? So the radius function was maybe, no, I don't. That was this, what we called psi HR before. And we'll use 3 ingredients to get a lower bound for what? So connecting the origin in the level set above level H to the boundary of the ball of radius R. That's what we're going to do. On the one hand, we use a change of measure argument using entropy. We also use what I was referring to before already, isomorphism theorems. So that's essentially coupling Gaussian free fields and random interlacement process. So, well, here I put what it actually looks like, but if you haven't seen this before, I think it's not too instructive. In some sense, the nice thing that you can actually get from this is that interlacement processes actually involve random walk trajectories or diffusions on this cable system. That means you find a path going to infinity along which the local time of this diffusion process is strictly positive. And this is something that we can use in order to be able to also say something about connected components of E larger than or equal to H for H negative but close to 0. That's sort of what's happening here. So we try to get, or we do transfer connectivity properties of this interlacement local times to connectivity properties of the GFF. That's what's happening here. And we also need some kind of local uniqueness result at the critical regime for the interlacement process. So that essentially tells you that if you have 2 macroscopic components of the interlacement process, then if you take a slightly larger ball, these 2 macroscopic components are actually connected in the slightly larger ball. That is something that is also known, for example, in Bernoulli percolation, and it's also been proven in this interlacement process. So here, let me try to prove this by a picture. So what we want is, we want to connect the origin, 0, to the boundary of the ball of radius R. That's what we want to do, and we want to do so in the level set above a certain positive level H. So what we do is the following. We first of all explore the connected component of the level set above H within a ball of radius psi, where psi was the correlation length. So that means at that level, we are not yet fully recognizing that we are in a subcritical regime. So that means that still, like the exploration still hits the boundary of this ball with a reasonably high probability, or sufficiently, not too small, let's say, probability. So that means this here essentially comes for free, or for not paying too much, let's say. But the good thing about this is that this already is big enough for a random interlacement trajectory, which is the green one. So maybe let me continue here. So this red ball, or this red component, will be hit with probability not too small by a random interlacement trajectory. So that's the green thing over here. It's not really interlacements, it's some kind of killed surviving interlacement. So it's a modified process, which is sort of just tailor-made for this context, but the isomorphism still holds true, and it ensures us that if we can do the connection in the interlacement process, that's also fine. So that's something that comes just from this isomorphism theorem. So that means this component is hit by an interlacement trajectory, that is the green one here. And sorry, so once the interlacement trajectory has traveled far enough, so that's happening here for us, we can actually make the connection using these balls. And this is also where this assumption on the geodesic that I was dubbing as a technical assumption at the beginning, or like on the way, comes into play. So we do find a path going to infinity, which is in some sense geodesic, and along this path, sorry, we can connect using these interlacement processes IU2, and this what I was calling before sharp local uniqueness essentially ensures that if you have an interlacement process here, or a macroscopic component of it, and a macroscopic component of it here, then you can actually connect it in slightly larger ball, and this is what we're doing over here. So that we can do a couple of times, and this doesn't come at too high a cost, so we do have to force some shift in here in order to actually see this interlacement process. But the probability of doing so still is sufficiently good in order for us to get the lower bound that we actually want. So this is sort of the strategy in order to connect the origin to the boundary of the ball of radius r. So we first explore, then we connect to one trajectory of interlacements, and then we use the sharp local uniqueness. Okay, so I guess that was a little bit technical. I hope it still conveyed some of the ideas, and with this, I'm already concluding. So thank you very much, and yeah, please let me know in case there's any questions.
Hey, thanks a lot, Alex, for that very nice talk. Let's thank Alex first. Okay, are there any questions?
I have well, many, but at least just from this last part, how do you, I mean, just in dimension 3, you somehow feel that your interlacements are touching because they are Brownian-like, so they will hit each other. But how do you manage to do it in high dimension where, you know, Brownian motions do not hit each other?
Yeah, so here it's, I mean, that's still, so it's not in RD, but it's on the cable system. So that is still on what we denote by Z tilde D.
Yes.
And there it turns out that you still have, you also have this local uniqueness in dimension D equal to 4. But if you go to higher dimensions, we don't know yet. So that is also something that is, I mean, this here holds true for a dimension larger than 2, strictly larger than 2. So we can do these prefractals, which are sort of in between 2 and 3, up to and including 4. But then we don't, then it's not clear afterwards how to continue this. This is something we are thinking about.
So okay, so just to understand, so you got this result for D equal 3 and 4 in a way.
Yeah, I mean alpha strictly larger than 2, and I mean as long as we are sort of in the diffusive setting where nu is or where nu is alpha minus 2, we get it for alpha larger than 2 and alpha up to including 4. Right, or I mean it's essentially what we need is alpha larger than or equal to nu. That's the condition that we need. And that, I mean, if you're in the diffusive setting, you get alpha equal to 4, implies nu equal to 2, so you get 4 equal to 4. So that's the boundary case in the diffusive setting. And then if you're talking about prefractals, you have to check. But yeah, Euclidean setting up including 4, but not more.
And do you have some story about geometry of these sets? Like, you know, if you take H, and I don't know, like H decreasing with this, I mean, going to 0 with the size of the boundary, can you get some kind of scaling limit of the level set connected to the boundary, for example, on these stories?
Can you repeat the question, please?
So whether there are some scaling, whether there are some scaling limits of the exploration set connected to the boundary, where you make like the boundary of the domain going to infinity, but the H is also going to 0 with the right scaling.
Yes. So we did not investigate scaling limits, and I'm not sure. I mean, it has been done in that context. I'm not sure people look at it in transient dimension in the first place.
Okay, any other questions?
Yeah, I have maybe a general question, but I don't know if maybe I missed it, but why, what is this? Okay, really not about this, but more about what you were telling us about that. I mean, all these special things are known for this model, that the critical case is 0 and so on. So why? I don't see that in this sort of argument. So there's probably some sort of symmetry or that's very special to this problem, or is it just magic?
Sort of. Well, I mean, well, okay. So it depends on is the isomorphism magic or is it not? I mean, you know, it's if you get it, you usually do it like I don't know, you compute expectations of exponentials, so it's not too intuitive either. But I mean, once you have the isomorphism, at least you do get some more insight, but it's not. I mean, I wouldn't. I mean, it's not fully understood why it's actually 0. There's no. I mean, we don't have a clear, nice explanation for that.
Right. I mean, it's not like in Z2 where you can see that it should be 0 and then there's
no, exactly. That's a good point, right? I mean, exactly. So H equal to 0 corresponds PC equal 1/2. And if you're in Z2, you know, you have the crossings and, you know, either you cross this way or that way, and then that's about it. But I mean, intuitively at least. But here, we don't have such a nice explanation at hand.
Okay.
It just has to do with the Markov property, you know. So like because you have the Markov property, you can explore it in a Markovian way from the boundary. If you have a really big boundary, you can explore it. And if you can explore like lower than 0, then somehow your mean would not average out correctly. A certain. No.
Can you say again, please?
So what I mean is that it has a lot to do with the Markov property of the GFF, not even only with the isomorphism theorems, like the fact that H star is equal to 0. Should just have to
but okay, I wouldn't know that it follows directly from the Markov property. But if you have a nice argument, I would be happy if.
Yeah, I would think about it.
Yeah, I mean, if there's, I mean, anything in that direction, I'd be happy to know. I mean, if the, you know, that's a very good question, and a question we get more often than not. It's there's no, I mean, at least to me, there's no satisfying explanation for that. I mean, yeah, I mean, you can try to approximate your lattice by using boxes, and then you ground the boundary, and then you introduce some killing, and I mean, you can somewhat argue things, but it's not, I mean, so as Danielle said, I mean, it's not like for Bernoulli bond percolation in 2 dimensions. You think, okay, that all makes sense, and it's obvious in some sense, and here you can argue, and there are some heuristics, I guess, but it's nothing, at least to me, nothing that's completely satisfying. But if you, I mean, anyways, if you find anything, write me or do let me know, please.
And Alexander, what happens if you take a vector value GFF? So you take 2 copies, for example, of the GFF, and you look at the norm. Can you say something about the percolation stories over there?
You take the norm of, so you take 2 independent GFFs.
Yes, and then you study your age is like norm of the GFF is more than age.
I haven't thought about this. Well, I would probably I would okay. My first hunch would be that you still get that H tildes. Okay, maybe okay. I would have said that it might not change the parameter, but I haven't thought about it. I mean, okay, I haven't thought about it, so I can't really say. But it's so is there any physical relevance by asking this, or just?
Okay, yeah, for us there is, because you know, when you condition a GFF, I mean, on its norm, but you saying is an XY model, for example. Like if you have 2 of them.
Okay.
XY model story, and trying to understand the level set has to do with which points you are warm or you are hot in that. I mean, with the points where you are really warm in your model. You want to understand these preparation stories.
I haven't thought about it, but yeah, I haven't thought about it.
Thank you.
Okay, so I have a final question. Already too late, but so Alex, I mean, does it make sense to kind of look at this for maybe non-transient graphs like d = 2 or something like this? Can you make sense of it?
Yes, you can. Yeah. So okay, so what you would have to do is you would have to, essentially what you do is you kill on the boundary. So if you, that's a little bit like the picture that I had before by Lauren Cook. And then in some sense you would so you would have to ask what's the probability of say connecting to the boundary.
Okay.
Right? I mean, if you think about percolation, right, so then you would ask about connecting to the boundary, and so there's also results. So on the one hand, that's also John Ding and co-authors, and then together with Alexi and Ole Elias, Johan Tykesson, and Fredrik Wiklund, we've also been sort of working on related questions.
Okay. Good. Okay, so if there are no more questions, then let's thank Alex again. And okay, that's it.